Right, well, I'm going to share with you some of our work at the user experience, how we use artificial intelligence for user experience. So I work at Daimler R&D office in Silicon Valley. We are in Sunnyvale. We have a group of engineers and data scientists and artificial intelligence gurus actually working very heavily on multiple topics. And I picked up one of the topics to share with you today. And as we go through the presentation, please feel free to pick up the questions and ask questions even after the presentation is over. This is SLR vehicles, it's SLR 300 at one of the racing events in Italy about a couple of years ago. And just from the look of the picture here, you can see how much people are really fascinated with the car and how much people have these emotional attachments to the car. And what we look at our job every day and think about our job every day is that how we can keep that for the future, how we can maintain this in the future. And the future is based on intelligence. And what we're looking at very heavily is how we can bring this intelligent user experience so people can keep this fascination with the car and can still be very attracted to using the cars. So I call it intelligence on the edge. And the edge here, of course, is our vehicle. The vehicle is, once you develop something and put it in the vehicle is in the wild. And that is our edge. It's not a mobile device. It's not an IoT. It is the car here. And we have 5 different areas we're focusing on when we talk about user experience. The first one is behavior modeling, and I'm going to kind of explain them very quickly, but then I'm going to focus on one of them. But for behavior modeling, what you want to do as you're sitting in the car is to the car should understand what you're trying to do, and then predict that, and then make your life easier. So if you are checking the traffic every Monday morning, then it should know that and it just show you the traffic. So that's what it is. Adaptive UI, the car should know if it is you versus your significant other. It will show different things. If your kid is driving the car, it should show different things. And show different model of interaction. User identification is the first step for that. Well, the car needs to know who you are. So as you sit behind the steering wheel, the car immediately needs to realize who you are so it can find the model for you and for your behavior. Then action automation is if you actually develop the model to a certain level of certainty, you can decide to do that without asking the user. And that's a very critical thing that we're going to spend some time talking about today. When you are confident enough that you need to turn the heater on, maybe you can turn the heater on without asking the user if he wants that or not. How do you reach that is what we're going to talk about today. Then user sensing is another area completely, which is you're trying now to understand what the user is doing physically in the car. Is raising hands, looking right, looking left, checking the gaze, checking the eye movement, the head movement, and from there you can have a very kind of holistic picture what the user is trying to actually do. Is trying to open the doors, trying to turn on the light in the cabin, or what exactly the user is trying to do. So these are the areas. And all of that combined together will get you to something like this. So this is the interior of the car. This is what you see when you sit in our cars. And that specific picture is actually from Concept EQ. This is the EQ vehicle is actually the blueprint of all the vehicles that we're going to be producing, all electric vehicles that we will be producing in the coming few years. The Concept EQ was shown at, we took this and we created this and we showed at Paris Auto Show last year, and we brought it again to CES, and we showed that car at CES. And when we sat down and developed this user experience inside the car, the first thing, of course, it has to be impressive. You have to just sit down there and appreciate the colors and the design and the way it looks. But as you start interacting with it, you have to also appreciate how intelligent it is. And that is the focus of what we're trying to do. So we started working on this a few years ago, started working on this intelligence a few years ago. And at CES this year, we actually showed the first product for that intelligence. And that is a product for the user, for the behavior modeling. And I will be happy to just share it with you very quickly what this product is going to, or is doing actually. This is in the new C-Class. So if you decide to purchase our new C-Class, you will actually get that product and you will be able to experience it.
Artificial intelligence is the future of computing. Artificial intelligence is transforming everything around us. And now we've put artificial intelligence in our cars. Your car can now learn you and begin to predict what you want to do based on the habits it learned about you. Whether it's selecting your next navigation destination, music, or people to call, it's all just a single button press away. Here's how it works. The car can recognize the driver and uses contextual clues like current location or time to determine what action to recommend based on previously learned experiences. On a weekday morning, it can pull up the fastest route to the office. On a weekend trip with family, it can suggest a kid-friendly radio station. When the context changes, its suggestions change. And in the future, it will even be able to automate completely. Artificial intelligence is not just the future. Artificial intelligence is here today in your Mercedes-Benz.
So how did that happen actually? So if you look at putting something in the car, now we develop the model, we put it in the car, and then the car is released to the customer, and then the model has to behave in the wild, as we like to call it. And there are lots of challenges, and I want to share some of these challenges with you. The first thing is that you cannot actually assume you have connectivity, which is one of the basic assumptions that we all have today. Like everybody has a smartphone, and everybody assumes they are connected all the time. But the car is not connected all the time. All cars that we produce have connectivity. They have the ability to get connected. But as you're driving through mountains and forests and all of that stuff, you cannot guarantee connectivity. You cannot guarantee it's available. You cannot guarantee the bandwidth. You cannot guarantee the latency. So the model has to behave on its own. It cannot just call home and ask for some help. It will have to act on its own on the edge. It's battery powered, so we're very sensitive to how much battery consumption that we are taking through these calculations. It is actually using limited resources in the car. We don't have server farm in the car. Of course, we have the latest and greatest GPUs and CPUs, but still, it's not your server farm that you run AI on usually. And then the last thing, of course, is that we don't have control over that algorithms. Once we put it in the car, it has to train itself. It has to make decisions on its own. And that is really the critical part that I want to talk about a little bit more here. So we're starting from the standard cloud AI that everybody's familiar with. If you are using Google or Amazon or Netflix, what you do is that you have a user interaction interface, basically. It's like a web browser or a mobile device, and then you do something, and then everything goes to the cloud. And in the cloud, you have your model. You have the AI model in the cloud. You have the training happens in the cloud, and all the user data actually stored on the cloud. Going back to your lab or your office, you do the validation on the data that happens on the cloud, or the data that's stored on the cloud, and using the models that's stored in the cloud. So in this, of course, traditional AI, you always have a cloud-centric approach where everything happens in the cloud. And that actually makes so many of the problems a little bit easier. If you look at the other way, our life is that everything has to live on the edge. Everything actually has to be inside the car itself. So the car has its own user interaction. The car will have and has to have its own AI model running on it. The training and the user data all happens in the car, all stored in the car. All of these actions are actually happening in the car, and decisions need to be made inside the car without calling home, because you cannot guarantee that you actually have access to your, or calling back your cloud. What we do in this case in our lab is that we get a sample of the data during the development time. So we capture some data, we run few cars, capture some data, and do the validation to develop the model. But once the car is released, all the decisions have to be made actually inside the car after that. So this is the edge environment that we're living in. Now, one of the big things that we need to think about, how how does this model that we put in the car, we developed this model, of course, we trained this model in the lab, but once we put it in the car, that model now has to make decisions. How can we be comfortable that this model can make the right decisions? So we start, maybe look at a model that we created. This is a density function. The x-axis here can be anything, can be, let's say, time of a day. And maybe the y-axis here can be a probability of something. So let's say the probability density of something. Should I turn on, the user will want to turn on the heater or not. And if you think about it this way, you can look at, okay, at certain time of a day, there is high probability that the user want to turn on the heater. Let's say this is the correlation here. And if that is the correlation, it will be easy to say, okay, well, if you have higher probability, then you turn it on. If you have lower probability, don't turn it on. The reality of it is that we don't know if this is actually accurate or not, because there is something else that plays in the background. It's uncertainty in that model. That model was developed in the lab, but it's developed in the lab using a certain data set. Now, as we release this model in the wild, it faces new challenges that we haven't encountered yet, we don't know. And there are lots of other things that are happening in the wild that we don't have control of. So there is some uncertainty in that model. And we need to actually know that uncertainty also before we make a decision, before the car makes a decision. Because actually, in this case, the edge device, the car, is making the decision. So we need to know if the uncertainty is low, we can trust the model. If the uncertainty is high, maybe we shouldn't trust the model. And maybe we should consider that when we decide what to do with this information that we have. So I'm going to take you to how we make that decision. So the decision to automate. Again, to continue on that example that we have, we're trying to understand now, should we start the heater or not? Just an example. And you can apply this to anything. Should you show traffic or not? Should you turn right or left? I mean, all the things that are happening with the intelligence in the car follows more or less the Markov decision process here. And it is a standard thing that you're all familiar with. There is some state, and then you have to decide whether you want to automate or not automate based on that state. If you automate, you have to design your reward function. And in this case, in our case, for that specific example, our reward function is the inverse of cognitive load and annoyance. So if you make the wrong decision, if the car makes the wrong decision and starts the heater, and the user didn't want to start the heater, then the user will be distracted. So this is a cognitive load because something happening and he didn't want it. And then the user will be very annoyed. And so we need to model that. So our goal here is to have a reward equal 0. Basically, there is no cognitive load and there is no annoyance. And this is the ideal scenario, is that you actually, or the car did the action that the user was planning to do anyway. And in this case, your reward for being correct is 0. Now, this is actually that pass. So that pass here is the pass that you actually decided to automate, and this is the probability that the user was going to automate anyway, was going to take this action anyway. So in this case, your reward here will be 0. Now, this is the inverse of that. This is, you decided to automate, but the user actually was not planning to do that. The user was not or didn't want to turn on the heater. And in this case, you get the inverse of this, and that reward function should be really, really negative. Very negative, so it can stop the model from doing that. So this is the reward for being wrong. Now, if you decide not to automate, let's say that the car decided not to automate, decided not to show or not to turn on the heater at this point. It can do so many things. It maybe ask the user, do you want to turn on the heater or not, or maybe just not show anything. But there are multiple cases here from 2 to n, multiple cases for if you decide not to automate what you will do. In any of these cases, or most of these cases, you want the expected reward to still be negative, but not so much negative. You just need it to be negative in order to make sure that the 0 is always your best case scenario. So we have 3 possible outcomes from this decision. Now, if you look at this, to find like the expected reward of automating or not, it's basically the reward of being correct multiplied by the function of being correct, or the probability of being correct, plus the reward of being wrong multiplied by the probability of being wrong. So this is basically the expected reward of automation. So at any point of time, the algorithm needs to look at, okay, well, should I automate or not? It will calculate this value. It will need to know the value of all these parameters here. Now, we have some other methods to estimate the reward of being correct and the reward of being wrong. But what we want to look at here is, how do we know the probability that the user will actually take this action or not? Because that's what we need to have in this equation here. Because if we know that, if we know the probability that the user would have taken this action anyway, we can easily calculate this function, or at least understand the estimation of the reward. If you look at this equation, what you want here, you want that if the expected reward of automating is larger than the expected reward of not automating, then the decision is, yeah, to automate. But to get to that, you need to actually get this function to be high enough. The probability that the user will have taken that action anyway, you need this to be high enough. And if that is high enough, then you will decide to automate, or the model in the car will decide to automate. Now, how do we know that? We will never know that. We can't read the mind of the driver. We cannot actually know if the driver would have preferred to turn on the heater or not, would have preferred to see the traffic or not, or we don't know. We cannot get this value. But what we can get is we can get the p-hat. And as you know, the p-hat is more or less, can be approximated to be the actual probability here. So we get this p-hat by actually looking at the training time, looking at the distribution. And we can get that p-hat from that. And if we know that p-hat, then what we can start looking at is we can look at the B pessimistic, which is basically the distribution function that you have minus the uncertainty. So every time I need to make a decision, I need to look at the probability, and I need to take the pessimistic value of this probability, which is the probability minus the uncertainty. And based on that, I can decide if I take an action to automate or not. So it comes to a point that I need to understand really the uncertainty in the model that I'm putting in the car. And this is the critical part. If I understand that uncertainty, I can make decisions to automate or not automate. Let me take you to process of estimating that uncertainty. How do we estimate that uncertainty? So first, I'm just going to quickly remind you with the dropout concept. So for you, some of you who are doing actually deep learning, doing neural net, you know of course that there is a well-understood concept there that if you use the dropouts by applying some distribution on the nodes, on the weights of the nodes, if you apply the Bernoulli distribution on the weights of the nodes, you can actually get an estimate for the remaining nodes, for the weights of the remaining nodes, and then use this information to run the second forward pass into this and get a better weight and so on. And from there, you can actually come up to a very good estimate for the weights in the network. So that concept is well known, well understood. It's used in neural net all the time. But what's interesting actually is the new idea that came a few years ago by Yarin here. And the idea is if you apply the dropouts in multiple forward passing or pass forward in your model independently, if you apply that independently, so the first time you applied is independent from the second time you applied, you can actually get samples of the, you can create samples from the learned posterior distribution. So you can create multiple samples here from that distribution. And from these samples that you created, you can actually estimate the variances, the moments. You can get the moments from there. If you come to this point, once you have the moments, you are actually estimate the uncertainty in your distribution. So we apply that, and the critical part here is that requires at inference time that requires you to actually run this process multiple times at inference time. So you need to run this at inference time multiple times. You need to run it in multiple independent instances. That actually lends itself very, very well to a GPU architecture, because you can run multiple of these processes in a way that they are independent. You can parallelize this. As you get stronger or better hardware, you can actually run those faster, and you can run them, you can run many of them so you can get a better idea of the uncertainty. So what we talked about here, and this kind of my last slide, more or less, the summary of it is that it's very important if you have a model on the edge making decision on its own to understand the uncertainty of that model. Very, very important. And you can do that using the dropout method. We can do that actually very, very well on a GPU, because you can run this in parallel, and you can scale this up, make it faster and better with a more powerful hardware. So I will leave you with the words from our chairman, Dr. Zacha. So this is the goal, actually, for all of this. The goal of all of this is to come up with a car that actually acts as a digital companion for you. It understands you. It can predict your move. It can actually learn your habits. It becomes a companion. And this is basically or that's basically our goal for all the work we're doing for artificial intelligence in our office. Thank you very much.
So we have a few minutes for questions.
Sure.
So if I can ask the first.
Please.
When we had dinner together, it was quite intriguing when you talked about the idea of what's real and what's hype. And why don't you just enlighten us? So I know all this is real and is fantastic, but give us the hype. What should we be concerned about when we hear people talk about the car knowing you and how it's going to make your life better and be your guardian angel and be autonomous? Where's the hype, and what should we be concerned about? And when is all this going to hype go away?
I think the hype in artificial intelligence is all around us. I mean, anybody who's here writing algorithms know exactly what the machine can do and what the machine cannot do. The machine is very good in doing lots of calculations and doing in focusing on a certain task and doing it very well. So you can actually identify images probably at the certain quality that matches human, or even in some cases better than human. But that doesn't mean the machine is better than human. I think human is a collection of different things that we call intelligence, and the machine can be intelligence in one of those areas, but not in all of them. The claim that the machine one day will be more intelligent than human, I have some doubt about that personally, but you're all entitled to your own opinions.
A couple glasses of wine, he'll tell you even more. Yeah. So we have time for, I think, one. Sir?
Do you see the need for specialized chips for the edge, or do you think kind of a centralized GPU can do all the processing that's necessary?
It depends on the use cases. So in the car in general, what we do is that we always split the machine critical or mission critical from infotainment, entertainment, navigation. So if the car needs to decide to turn right or left or to stop, that's a different mission from if the car needs to play this song or that song. So far, we keep those separate. So far, we keep the processing separate because we want one of them to be 100% reliable, and there is no room for error, and the threshold for decision is extremely high, and the other one is a little bit more, let's say, forgiving. So that decides part of it. I think if you look at where the processing power is going in GPU and in other, I think we'll come to the point where you might be able to run everything in one from the processing power itself, if you just focus on that. But I think the decision in the car, at least, will depend on other things. It will not depend on the processing power itself.